Just to give you some ideas of other things that this first part of the fundamental theorem of calculus can do for us. And this is really not something that we're going to be focusing on in this class, but whatever. Let's consider a function like f of x here, which is the integral from 0 to x of sine of pi t squared dt. Something about this function is there's no way for us to find this antiderivative of sine of pi x squared, at least in terms of functions that we already know and deal with. So in fact, we could take this as a definition of this function f of x. That's kind of the best we can do. And we'll learn some ways that we can approximate functions like this. But we can still tell a decent amount about this function, given that we know that its derivative is sine of pi x squared. So for example, we can figure out when its horizontal tangents are, which is pretty important for graphing it. These happens when sine of pi x squared is equal to 0, which happens when pi x squared is equal to 0, pi, 2 pi, 3 pi, whatever, which happens when x is equal to 0, or plus or minus the square root of 1, which is 1, plus or minus root 2, plus or minus root 3, etc. Furthermore, the first derivative test tells us when we have maximums and minimums. At 0, the derivative goes from positive to positive, so there is no minimum or maximum. You might call that a saddle point. However, for 1, negative root 2, root 3, etc., the function goes from increasing to, the first derivative goes from increasing to decreasing. So we have maxima at these points, and we have minimums at negative 1, root 2, negative root 3, etc., because that's where the derivative goes from negative to positive, so we have minimums. So we can tell a decent amount about the properties of this function. We could also take the first derivative of sine of pi x squared, which would be, well, go ahead and figure that out maybe if you want to. And that could tell you something about the inflection points of this function f, where it's concave up, where it's concave down, etc. So we can tell a lot about this function f of x, even though we really don't have much more of a hold of it than defining it to be this integral. All right, this next sort of problem is really just a good way of understanding sort of the mechanical aspect of the fundamental theorem of calculus part 1. So for example, let's evaluate the derivative with respect to x of the integral from 0 to x squared of the natural log of e to the t plus 1 dt. So if this were just x, fundamental theorem of calculus part 1 would say the derivative is just the inside function with t replaced by x. But this is really a function within a function. It's not evaluating this integral at x, it's evaluating this thing at x squared. So the chain rule says, well, let's replace this sort of inner function x squared with the expression u, and then this is equal to the derivative with respect to u of the integral from 0 to u of log of e to the t plus 1 dt times du dx, where u is x squared. Okay. So now our inside function here is really x squared because it's appearing inside of this limit of integration. The outside function is this cumulative area function type thing. So we find the derivative of this expression with respect to u is, by the fundamental theorem of calculus, log of e to the u plus 1. Du dx is 2x. And so finally, replacing u with its expression x squared, we get 2x log of e to the x squared plus 1. And just to give you the fun of doing this sort of thing, let's evaluate the derivative with respect to x of the integral from 0 to log of x e to the t squared plus 1 dt.